Hi, welcome back. We're in Lecture 14, and the topic of Lecture 14 is mediation. In the first segment, I covered mediation according to the standard approach, which is to run a series of regression analyses. In this second segment, I want to show you how a mediation analysis could be conducted under the framework of structural equation modeling, which is a more advanced topic in statistics and beyond the scope of an introductory course, but I can give you a glimpse of how structural equation modeling works in this section on mediation. So in this segment, let's look at mediation conducted as a path analysis. So the results of mediation analyses, if you see them reported in journal articles or online or sometimes in the news, rarely you'd see them reported in the news, but perhaps. You might see them reported as what's called a path model, a graphical model that depicts the results of those regressions that we ran in the last segment. And path models are a form of structural equation models, again, which is an advanced topic in statistics. In most universities in the US, for example, structural equation modeling is a semester-long course that's typically taught and reserved for graduate students. So it's a pretty advanced topic, but I'll give you a glimpse of it here in this segment. These path models are graphical models, and they have a notation or grammar, if you will. So rectangles represent observed variables, so the variables that we actually measured. So like x, y, or m, like the working memory measure or the IQ measure. Those are represented by rectangles. Circles represent unobserved variables, so things we just can't observe or don't see. So in this example, the only unobserved we have is the error term. We can't see the error, it's unsystematic, we don't know what it is, so we'll represent that with a circle. Triangles are used to represent constants, and then arrows represent associations between variables. So like from x to y, for example. And I'll have more to say about exactly how you draw those arrows as we go through these models. So let's start with the simplest path model that's possible, and that's a simple regression. So you see the equation for simple regression, and this is how we would represent it in a path model. So here's our outcome variable y, and what we're saying is y is influenced by x, and to what degree is it influenced by x? Well, that's represented by the slope b1, which relates x to y. And then, of course, we're always going to have some prediction error or residual, so that's out here. That's the error term. Remember, in the regression equation or in the model, there's also the regression constant. So I have that represented here by a constant 1 times the regression coefficient b sub 0. So that's just how we can represent everything in a graphical model rather than through a series of sort of complicated and tedious regression coefficients. Just put it all right there in a path model. It's a nice illustration. One thing to note about the arrows, so I said influence, x influences y, because I want to be cautious. But in true structural equation modeling, what a directional arrow like that implies is causality. Okay, so this is where people start to slip and start to make causal claims from correlational data. So let's just be clear that if we're dealing with correlational data and someone puts that directional arrow in there, take it with a grain of salt. We're still dealing with correlational data. But what that implies is causality. X is causing y. So here's a slightly more complicated path model, but still very, very simple. And this is just to illustrate mediation. And I think this is a very nice and efficient illustration of mediation. And this is why I'm introducing this topic here in this lecture, because as I said, a lot of researchers will present this kind of path model to illustrate the results of their mediation analysis. So remember, according to the mediation analysis, our predictor variable is causing or is predicting M, and then M is predicting Y. And the question is, what happens to that direct path? When we add in the mediator, does it go from being significant to non-significant, or does it just drop, or does it not change at all? So to avoid confusion, and this is a very common step in mediation with path models, we could put labels on the paths. So, and again, I'm just sort of following convention here. The path from X to M is typically given the label A. From M to Y, we call that B. The direct path is typically given the label C before we add in the mediator, and then C prime after adding in the mediator. And note here that AB, A times B, that's known as the indirect path. So it's the indirect path from our threat manipulation to our outcome, the IQ score. It's indirect because it's going through the mediator. So here's the path model without the mediator. I'm going to just call this C. And here's the path model with the mediator. I'm going to change that to C prime. And of course, critical question is going to be, what's the difference between C and C prime? But also note that I have A and B, and A times B is the indirect effect. So now we can just rewrite those three regression equations, just substituting the labels instead of the actual variable names. So these are just the three regression equations that we ran in the last segment, just showing you the same thing with the labels. The reason I wanted to wait on this Sobel test, I didn't cover it in segment 1, I'm covering it here in segment 2, is now it's a lot easier to explain what the Sobel test is doing now that I have labels on these paths. So the Sobel test is testing the effect of the indirect path. That is the indirect path from X through M to Y, is that statistically significant? So it's a null hypothesis significance test, where the null hypothesis is that the indirect effect is 0. Okay? It's really important to remember that. A lot of people forget, and they think that the Sobel test is testing the change from C to C prime. It's not doing that. It's testing the null hypothesis that the indirect effect is 0. If we get a nice strong indirect effect indicating mediation, then we'll reject that null hypothesis. Here's the formula. It's not really critical that you know the math underlying this, but you can see it's just like any other sort of NHST. It's a ratio, basically, of what we observed relative to what we would expect. And what we observed was an indirect path where it's the unstandardized regression coefficient for A times the unstandardized regression coefficient for B over standard error of those. It's a little bit complicated, but again, it's essentially a ratio of what we observed relative to what we would expect due to chance. If we get, say, sort of 2 or 3 times more than what we would expect due to chance, then we're going to reject the null. So again, now let's look at the results. You already saw the top part of this, so now let's go down to the bottom part. This is where the Sobel test results are reported. So you see R calls it the indirect effect, because that's indeed what we're testing is the indirect effect. And it gives you a regression coefficient, that negative 8.59, but that's just the regression coefficient for the path that we labeled A times the path that we labeled B. That number, 8.59, is not that critical. What's more important is the z-value, which is right here, which is negative 3.87, and that's significant. So to be significant with alpha of 0.05 in a z-test, we need a score beyond 1.96. We're well beyond that. It also reports the sample size was 100 in this case. We had 50 subjects in the threat condition, 50 in the control condition. So that's the other piece of evidence suggesting that we have a really strong mediation effect here, is we have a really nice Sobel value that's significant. Now what I can do is take those regression coefficients from the R output and now put them on the path models, and this makes it much, much easier to sort of understand what happened in this experiment. So this is how I would report the results if I were presenting this work, for example, at a conference or something. I would say, well, we did this experiment where we manipulated stereotype threat. We had a threat condition, a control condition. Did that impact IQ? Well, yes, it did. In fact, people in the threat condition scored on average 11 points lower on the IQ test than the students who were assigned to the control condition. And that 11-point drop was significant. We saw that from the R output. The 97.32, that's the predicted score on IQ when all predictors are 0. Right? So in this case, that's just the controlled condition. So that's right about average. This is a pretty strong effect, and in fact, it's representative of real research. Stereotype threat effects are very strong. You can get as much as a 10-point drop. And then I would show a model like this to illustrate the mediation. And what you see is that 11-point drop is now only a 2-point drop. And why is that? Well, because working memory capacity is accounting for that effect. And you see that here with this nice strong effect of threat on working memory capacity. So there too, there's like an 11-point drop as a result of the threat manipulation. And then working memory capacity predicts IQ, and looking back at the R output, that was significant. And looking at the Sobel test, we know that this indirect path is significant. So I would also note that if I was presenting this, I might put the Sobel stats sort of on the side to show the Z value and show that it was indeed significant. So this is a nice way of illustrating the results of mediation. But here, all we did was use a graphical model to just illustrate the results. I still just did a series of regression analyses, right? So I didn't actually do structural equation modeling per se in this example. We could do a different kind of analysis. You wouldn't run the 3 LMs. You would actually run a model called structural equation modeling. You would need a different package. There are a few in R. One is Lavon that I like. Another is MX Plus. There are a few. And what you can do is put that whole model in. Let's go back to the graphical model. You can put this whole model in and say, does this model account for all the correlations that exist among these variables? And if it does, then that model is said to fit. And you would then test this model versus one where we take out the direct path. So can I still account for all the correlations without the direct path? And you compare the fit of those models, sort of like we compared the fit of models in the moderation lecture. And if I can account for all the variables and all the covariances among these variables without the direct path, that implies that I have full mediation. We don't need that direct path. That's how structural equation modeling works. But again, it's sort of beyond the scope of an introductory class. But again, mediation is a place where it allows me to sort of provide a glimpse of structural equation modeling. It's a very popular and powerful tool in statistics. So if you're going forward in statistics, I highly recommend a course on structural equation modeling.